Hello students, in the previous video you have studied what is dispersion, what is spectrum. Okay. Now Newton was the first scientist who obtained the spectrum of white light through a glass prism. When he obtained the spectrum for the first time through a glass prism, he thought that maybe the glass prism is responsible for creating those 7 colors, for creating the spectrum. Okay, he never believed that, he was not accepting, or he never believed that the colors are present in the white light. What he thought was the colors were created, or the colors are created by the glass prism. So he thought maybe by using more prisms, he could get the spectrum of more colors. He tried to do some activities by using more prisms and by placing them close to each other, keeping them at different positions with respect to each other. He didn't succeed in that, but what he obtained was that this recombination of the spectrum of white light. So instead of getting the spectrum of more colors, instead of splitting the spectrum of white light which he obtained by one prism into more colors, getting the more beautiful spectrum, what he obtained was white light again. So let us discuss this activity which actually was performed by Newton, which gives us the recombination of the spectrum of white light. Indirectly, this activity proves that prism is not creating 7 colors, but the 7 colors are already present in white light. So let us see the activity. Now here we have 2 identical prisms which are closely placed, and they are placed such as they are placed inverted with respect to each other. So these 2 are glass prisms placed inverted with respect to each other, close to each other as shown in the figure. Here we are getting a very narrow beam of white light which enters into this prism, and suppose we know that if we place a screen here, we can get the spectrum of white light. But again here the second prism was placed very close to this, and on the other side of the second prism, a screen was placed on which white light was obtained. It means, so this white light is splitted by this prism into 7 colors. Spectrum here, which is again incident on the second prism, it again recombines, the colors recombines again to get the white light. And on the screen, instead of getting the spectrum, here if we have a point source of light, then again that point color image, bright image is formed there. So this activity is, we can say, proves that white light contains 7 colors. The colors are not created by prism. Okay, so recombination of the spectrum of white light can be explained by this activity which actually was performed by Newton. See, when you draw this, there is no need to draw all the 7 rays here of different colors. You can just show the extreme colors, violet and red. See, here the white light is splitting into the spectrum with violet at the bottom and red at the top. Okay, and the bending is towards the base. Again at these points, the bending is towards the base only. So on this prism, when they strike, they are bending here again towards the base. See, this is the base of the second prism. Okay, and here you have to show that they recombine, and finally the single ray you will show here, although single ray is actually never possible, but on the paper we show a ray. So again we get white light beam or white light ray, and so there is screen which you can show it there. Okay. So I hope you have understood this activity once this activity had come in the board exams also. Now let us discuss few important points related to light. As I have told you before also, when light travels from one medium into another, its frequency remains constant. Frequency of light does not change, but what changes? Its speed and wavelength. So remember, this is very important point, that what happens when light travels from one medium into another? Its frequency remains constant, but its speed and wavelength changes, and also bending of light takes place, as you know. So we can say velocity changes. If you remember the equation that you have studied in your 9th class in the sound chapter. So V is equal to F lambda you have studied in the sound chapter where V is, we know, velocity or speed of sound wave, F is frequency of sound wave, and lambda is its wavelength. Okay, and if you remember, two types of waves were discussed, transverse waves and longitudinal waves. Sound, we know, is a longitudinal wave, and it was just mentioned in 9th class that light is a transverse wave. So now also you remember that light is an electromagnetic wave and it is a transverse wave. Although we will not go in detail, but still you can remember that light is an electromagnetic wave and it is a transverse wave. So V is equal to F lambda is also valid for light. Okay. Now VR is equal to FR into lambda R. For red color, I can write the equation like this. Let us write the same equation for violet color. VV is equal to FV into lambda V. In vacuum or in air, all the colors move with the same speed, that is C. So instead of VRVV, I can write C is equal to FR lambda R, and it is also equal to FV into lambda V, because speed of red color, violet color, in fact all the colors of light is same in vacuum, or in air also we consider it to be same only. Okay, so from this equation we see that the speed is constant. It means the product of frequency and wavelength of each color is constant. But remember, the product is constant, not their frequencies and wavelength. Okay, just remember this VIBGYOR. VIBGYOR is the acronym to remember the sequence of colors in the spectrum. As we move from violet towards red side, lambda increases. It means red color has the longest wavelength and violet has the smallest wavelength. So smallest wavelength is possessed by violet. And if this product is constant, and if we say red color has the maximum longest wavelength, so obviously it is having minimum frequency. So we can say for a given color, frequency and wavelength are inversely proportional, because from here we can write that F is equal to V upon lambda, or FR is C upon lambda R, and FV is C upon lambda V, where C is a constant. So we can say frequency and wavelength are inversely proportional to each other for any color of light, in fact for any wave. So red color, which has longest wavelength, has minimum frequency, and violet color, which has shortest wavelength, has maximum frequency. So lambda increases when we go from violet to red and frequency decreases. Please do remember this. Okay. Generally, whenever we say wavelength of red light is this, we mean in air or in vacuum. Because as I have told you that when light travels from one medium into another medium, frequency remains constant, but the speed and wavelength changes. So obviously wavelength of light is, any color of light is not fixed. It changes with the medium, and speed and velocity also changes, because speed, magnitude as well as the direction changes when light changes its medium. So in vacuum we can write C is equal to F lambda. In other media we can write V is equal to F lambda. F is constant. When V decreases, lambda will decrease. When V increases, lambda will increase. Remember this. So if I ask you which color has minimum wavelength in glass, so you have studied this in the previous lecture, which color has minimum speed? Violet. When violet has minimum speed, it has minimum wavelength in glass, and red color has maximum speed or magnitude of velocity in glass. So maximum speed means it has maximum wavelength. I hope you will remember these concepts clearly. Okay, and now let us continue with this. So now let us see what is total internal reflection. Okay, so to understand this, we will consider two different media, air and glass. See, I have written first here and second here. means our incident light lies in first medium. Okay. So consider here, please don't consider white light, consider a single monocolor of light, it means monochromatic light. So if a ray of light, monochromatic light, is traveling like this in the glass and it strikes the boundary separating the two media, you know it will enter into the second medium. If it is incident, this is a case of normal incidence because this itself is a normal. So when the ray is incident normally, there will not be any refraction taking place. It means ray will not bend, it will travel along the same path in the second medium. Okay. Now let us, so here what is the value of I? Angle of incidence 0, because angle of incidence is angle between the incident ray and the normal. So here normal and incident ray, they are lying on the same line. So I is equal to 0 degree. Let us increase the angle of incidence as I have shown here. So here I have increased the angle of incidence. I is having certain value. It is not 0 degree. And then if this is my incident ray, I know that part of the incident light will reflect back following the laws of reflection. It means here if I write IR, then I will be equal to R, angle of incidence will be equal to angle of reflection. So part of the incident light will reflect back following the laws of reflection, and part of the incident light will enter into the second medium. Again we'll know it will follow the laws of refraction, and as the light is traveling from glass into air, from optically denser medium into optically rarer medium, so the ray should bend away from the normal. So here this dotted line represents the original direction of incident light. This is our normal, so the ray will bend away from the normal. And here I have written R. R is the angle of refraction. Because R is used for angle of refraction here, so I have not shown here R. But you know this is the angle of reflection. Okay. So let us continue. Let us continue to increase the angle of incidence and see what happens. Now if I increase this I still more, okay, slowly I will keep on increasing this I. So I have increased the I here. Again the same thing will happen. Part of the light will be reflected back, okay, following the laws of refraction, and part of the light will refract away from the normal when it enters into the second medium. So if we continue, I have not drawn many figures here, but you can imagine that as we increase I from 0, slowly what is happening? Part of the light is reflected back into the glass and part of light enters into the second medium air, but it is moving away and away from the normal. So if we keep on doing this, slowly, gradually what happens? Let us say for one particular value of I have represented it by IC. Okay. Part of the light again reflects back into the same medium, that is glass, following the laws of reflection. And now our refracted ray, if I increase it slowly, this thing will continue to happen. But for one angle of incidence IC, this refracted ray which is moving away and away from the normal, for one particular I, that is IC, this refracted ray, see I have put an arrow here, it lies along the boundary separating the two media. It means it lies along the interface of the two media. So in this case our refracted ray is neither lying in the first medium nor in the second medium. It is lying along the boundary separating the two media. So what is the angle of refraction in this case? That is the angle between the refracted ray and the normal, and it is, we can say, 90 degrees. Okay. So let us proceed further and see what we can expect, and logically I think so you will accept here what I say. If I increase I more than this, let us say I am increasing this angle of incidence and I is greater than IC, then what will happen? Now refraction will not take place because already this was it was going away and away from the normal. So for IC it was lying along the boundary separating the two media and R was maximum 90 degree. It means if we increase our angle of incidence more than IC, what will happen? The entire incident light will reflect back into the same medium, that is glass, following the laws of reflection, that is I is equal to R. In the last figure, R is the angle of reflection. So we can say no refraction takes place there, only reflection takes place. In the mirror also, whatever light is incident, all the light reflects back. But mirror has a special property of reflecting all the light back for all the angles of incidence. But in this case, this happens only when I is greater than IC. And this phenomenon is called as total internal reflection. So it is different than the common reflection that we see in the mirror. Okay? Total internal reflection is a phenomenon. Now first of all, let me define this IC. What is IC? IC is called as critical angle of incidence for a given pair of media and for a given color of light. It means this IC value is fixed for a given pair of media and for a given color of light. If you repeat the experiment with different color, okay, then the IC value will be different even if you keep the pair of media same. For different colors of light, this IC value will be different. What is IC? Critical angle of incidence for a given pair of media for a given color of light. It is the angle of incidence in the denser medium when angle of refraction in the rarer medium is 90 degrees. This is its definition. So critical angle of incidence is angle of incidence in the denser medium when angle of refraction in the rarer medium is 90 degree when the light is traveling from denser to rarer medium. Okay, and we know that this value, critical value, angle of incidence value will change. If we change any of the two media, if we change, the value will change, or even if we change the color, the value will change. It is fixed for a given pair of media and for a given color of light, as we state Snell's law of refraction. Okay, and here do remember that when the angle of incidence is less than critical angle of incidence, then both the things are occurring at the same time, reflection as well as refraction. Now here also students, so remember, when the angle of incidence is less than the critical angle, in all the cases, even in this case, part of light is reflected back and part of light gets refracted. See, okay, so in this case the reflected light is never very intense, because intensity, or we can say, and although energy and intensity are not the same physical quantities, but intensity and energy, they both are related somehow. Okay, so more intense light means having more energy. So here if we consider here incident ray of light, so this intensity or energy of this light is divided into two parts, because incident ray gets split into two rays, one reflected and one refracted. So here the intensity is getting divided into two parts. So in this case the reflected light is not very intense. But when the total internal reflection takes place, that is when I is greater than IC, when no refraction is taking place and all the light reflects back into the denser medium, in that case our reflected light is very, very intense. It is almost as bright as our incident light. There is no loss of intensity. Entire intensity of light is reflected back into the same medium. So students, you should know the definition of critical angle of incidence, which I have told you now, and total internal reflection. You can define total internal reflection as a phenomenon in which when light is traveling from denser into rarer medium, if the angle of incidence is greater than the critical angle of incidence, then the entire incident light reflects back into the denser medium. This is called as total internal reflection. Suppose if I ask you, give two conditions for necessary conditions for total internal reflection to take place, then you should write these two conditions. One, light should travel from optically denser to optically rarer medium. Second, I should be greater than IC, that is angle of incidence should be greater than critical angle of incidence. as you have seen here. You know, had it been air here and glass here, then what would have happened? The ray would have refracted towards the normal. So towards the normal means as we increase I, the ray would be moving towards the normal. So in that case, total internal reflection is not possible. So remember what is total internal reflection, what is critical angle of incidence, and what are the two conditions for total internal reflection to take place. I hope this topic is clear to you, because rainbow formation has this phenomena in it. This phenomena is responsible in the rainbow formation, and we'll discuss rainbow formation in our next class. Hope the video is clear to you. Thank you, students.